The universe just whispered its deepest secret. That sound you might have heard was the echo of two black holes colliding over 1 billion years ago, a ripple in the very fabric of space and time known as a gravitational wave. These cosmic messengers carry stories from the most violent and energetic events since the dawn of the universe. In this journey, we will uncover 50 incredible facts about these extreme gravitational waves, taking you to the crushing edges of black holes and back to the first moments of existence. You will discover how the gold in a wedding ring was forged in a cataclysm more powerful than 1 billion suns, and why physicists are listening for the faint hum of the Big Bang itself. What does it feel like to hear the cosmos ring like a bell? That faint cosmic whisper finally reached Earth on September 14, 2015. After a century of searching, scientists at the LIGO observatory detected a signal so profound it shook the foundations of physics. They called it GW150914, a name born from the date of its discovery. This was the first direct proof of gravitational waves, ripples in spacetime that Albert Einstein predicted all the way back in 1915. For 100 years, his theory of general relativity had told us these waves should exist, but they were so incredibly faint that catching one seemed almost impossible. The signal told a violent story. It was the death spiral of two black holes, each over 30 times the mass of our Sun, locked in a final, furious dance over 1 billion light-years away. As they circled closer and closer, moving at half the speed of light, they stretched and squeezed the very fabric of the cosmos, sending out these tremors. What the instruments recorded is known as a chirp, a rapid increase in the wave's frequency and amplitude. It is the sound of spacetime itself ringing. In just 0.2 of a second, the pitch of the chirp soared as the black holes completed their final orbits and merged into a single, more massive object. The energy released in that instant was staggering, outpacing the combined light of every star in the observable universe. This was not a discovery made in isolation. It was the culmination of decades of work by over 1,000 scientists across the globe, a testament to human curiosity and international collaboration. That single chirp marked the opening of an entirely new window on the cosmos, transforming our silent movie of the universe into one with a powerful, resonant soundtrack. We were no longer just stargazers, we had become listeners to the universe's most dramatic events. That single chirp was a vibration of spacetime itself. So what exactly are these gravitational waves that we are now detecting? Think of the universe not as an empty stage, but as a vast, flexible fabric. This fabric is spacetime, a single entity combining the 3 dimensions of space with the 1 dimension of time. Massive objects like stars and planets create dips in this fabric, which we experience as gravity. Now imagine the most violent events in the cosmos, like 2 black holes colliding. These cataclysms do not just create dips, they send powerful shudders racing outward. These are gravitational waves, ripples moving through the fabric of spacetime at the speed of light. Crucially, these are not waves traveling through space like light or sound. They are waves of space itself and of time. As a gravitational wave passes through you, it literally stretches and squeezes the space you occupy. Distances between objects increase and decrease in a rhythmic, undulating pattern. A simple analogy is dropping a pebble into a calm pond. The pebble disturbs the water's surface, sending circular ripples expanding in all directions. In a similar way, a massive cosmic collision disturbs the fabric of spacetime, sending ripples across the universe. But the scale of this distortion is almost incomprehensibly tiny. The gravitational wave that first reached LIGO stretched and squeezed our entire planet by an amount far smaller than the width of a single atom. Detecting such a minuscule wobble is like measuring the distance to the nearest star with an accuracy the width of a human hair. This is why it took a century of effort to finally catch one. We are listening for the universe breathing in and out on a scale so small it defies everyday experience. Those ripples in spacetime do not travel at just any speed. They race across the cosmos at the ultimate velocity, the speed of light itself. This is not a simple coincidence. It is a foundational rule written into the very code of the universe by Einstein's theory. Gravitational waves are not just moving through the fabric of spacetime. They are vibrations of that fabric, and they propagate at the universe's maximum allowed speed, a constant of approximately 1,086,000,000 kilometers per hour. This cosmic speed limit has profound implications for how we observe the universe. When our detectors here on Earth pick up a gravitational wave, we are witnessing the event in real time as it happened. There is no delay. The wave we feel from a collision a billion light-years away is a direct, immediate signal of that ancient catastrophe. This allows for a revolutionary kind of observation called multi-messenger astronomy. Imagine a cosmic crime scene. For the first time, we have more than one witness. We can have traditional telescopes that see the flash of light, neutrino detectors that catch elusive particles, and gravitational wave observatories that feel the shudder of spacetime itself. All of these messengers travel at the same speed, so if they come from the same event, they arrive at Earth at nearly the same moment. By combining these different signals, scientists can build a complete, three-dimensional picture of the most violent events in the universe, understanding not just the light show, but the underlying physics of the engine that created it. This is how we move from being mere spectators to true cosmic detectives. The energy unleashed in these collisions is almost beyond human comprehension. For a fleeting moment, the merger of two black holes becomes the most powerful event in the universe since the Big Bang itself. The gravitational waves radiating outward carry more energy than the combined light of every single star in the observable universe. Think about the sheer scale of that statement. Every galaxy, every nebula, every shining sun across billions of light years, all outshone in raw power by a single, invisible event. This incredible burst is not a flash of light or a torrent of radiation. It is a pure, violent shudder in the fabric of reality. All that energy is channeled directly into the gravitational waves, ripples that literally steal motion from the orbiting black holes. This energy loss forces the two colossal objects to spiral closer together, their orbits decaying in a runaway process. They whip around each other faster and faster, nearing half the speed of light in their final, frantic moments. This is the death spiral, a cosmic dance of mutual destruction. The gravitational wave signal we detect, that rising chirp, is the direct sound of this orbital energy being converted into ripples in spacetime. The final merger is the ultimate release, a storm of energy that briefly warps the cosmos on a staggering scale, all before fading back into an almost imperceptible hum. How can something so powerful leave behind almost no trace? That final, furious death spiral leads to a moment of profound transformation. When we talk about black holes colliding, the word collision can be misleading. These cosmic titans do not simply crash into one another like billiard balls. Instead, they perform an intricate final dance known as a merger. This process unfolds in three distinct acts, a cosmic drama written in the language of spacetime itself. The first act is the in-spiral. Drawn together by their immense gravity, the two black holes begin to orbit their common center of mass. As they swing around each other, they radiate energy away in the form of powerful gravitational waves. This energy loss is like a cosmic break, causing their orbits to decay. They are forced to spiral inward, moving faster and faster as the distance between them shrinks. In the final moments before the merger, they can be whipping around at nearly half the speed of light, a blur of ultimate darkness stretching the fabric of reality to its limit. The rising chirp we detect is the sound of this accelerating in-spiral. Then comes the merger itself, the second act. This is not a crash but a fusion. The two distinct event horizons, the points of no return, touch and then merge into a single, larger boundary. The result is a new, more massive black hole, but this newborn object is not yet stable. It is born wildly misshapen, like a wobbling droplet. It is not a perfect sphere, but a churning, turbulent form struggling to find its balance. Finally, we reach the third act, the ring down. Just as a bell rings with a specific tone after being struck, this new, wobbly black hole vibrates in a specific way. It shakes off its imperfections, settling into a smooth, stable, and silent sphere. It does this by emitting one last burst of gravitational waves, a fading hum that carries the unique signature of its final mass and spin. This ring down is the black hole's way of announcing its new identity to the universe, a single note struck on the fabric of spacetime before the silence of the void returns. That brief ring down after a black hole merger is the sound of silence returning. But sometimes the cosmic collision does not end in darkness. It ends in the most spectacular light show imaginable. On August 17, 2017, the universe delivered a perfect example. For the first time ever, astronomers detected a gravitational wave signal that did not come from black holes. The event, named GW170817, was the merger of two neutron stars. These are the incredibly dense, city-sized corpses of massive stars, each one containing more mass than our Sun, crushed into a sphere only about 20 kilometers across. A single teaspoon of neutron star material would weigh billions of tons. The gravitational wave signal told the story of their final, decaying orbits, a familiar chirp that drew the attention of observatories worldwide. But then, something unprecedented happened. Just 1.7 seconds after the gravitational waves arrived, orbiting telescopes detected a powerful flash of gamma rays from the same patch of sky. The gravitational wave window to the cosmos had just been thrown wide open, and for the first time we could see through it with light. This single event triggered a global astronomical effort, with dozens of telescopes swiveling to observe the aftermath. What they witnessed was a phenomenon known as a kilonova, an explosion 1,000 times brighter than a typical nova. For days, the point of light in the galaxy NGC 4993 glowed with an intense, shifting color from blue to a deep, profound red. This was not just a light show, it was a cosmic factory in action. The violent collision of the two neutron stars forged a cauldron of unimaginable pressure and density. Within this maelstrom, neutrons were ripped from the stellar corpses and slammed into atomic nuclei at incredible speeds. This rapid process, known as rapid neutron capture, is what builds the heaviest elements in the universe. In that single kilonova explosion, vast clouds of newly forged gold, platinum, and uranium were created and then blasted out into the surrounding space. Every ounce of gold in a wedding ring, every piece of platinum in a catalytic converter, and the radioactive heart of nuclear reactors, all were likely born in such a cataclysmic event billions of years ago. We are literally walking stardust, but the heaviest elements we carry come from the ashes of the universe's most violent and beautiful deaths. That rising chirp is a cosmic fingerprint unique to each cataclysm. When astronomers listen to this sound, they are not just hearing a signal, they are reading a detailed story encoded in the very shape of the wave. The chirp's rising pitch and growing volume tell a precise tale of mass, distance, and destruction. The frequency of the wave, how many times it oscillates per second, is directly tied to the orbital speed of the two objects. As they spiral inward, they orbit faster and faster, and the pitch of the gravitational wave soars in a perfect correlation. This frequency reveals the masses of the objects involved. Heavier black holes or neutron stars merge at a lower frequency, producing a deeper, slower chirp, while lighter ones whip around each other at a much higher pitch. It is like listening to a musical instrument where the size of the instrument determines the note it plays. The amplitude of the wave, its loudness or strength, tells us something else entirely: the distance to the event. A louder signal generally means the collision happened closer to us, while a fainter one indicates a source from the far reaches of the universe. But there is a twist. The amplitude also depends on the masses of the objects, so scientists must untangle these two pieces of information from the same signal. By carefully analyzing the exact pattern of the chirp, how quickly the frequency rises and how the amplitude changes, they can calculate not only the individual masses of the two objects but also the final mass of the merged remnant. They can even deduce the spin of the new black hole and the orientation of the entire system relative to Earth. From a single, fleeting whisper that stretches our planet by less than the width of an atom, we can reconstruct the final moments of a dance between two cosmic titans that occurred billions of years ago in a galaxy far, far away. Decoding that cosmic fingerprint reveals a fundamental truth about the universe itself. Spacetime is incredibly stiff. While massive objects like stars and planets create deep, stationary warps in this cosmic fabric, actually getting it to vibrate is an entirely different challenge. Think of it this way: a calm pond is easy to ripple, you just need to drop a small pebble. But imagine trying to create a visible wave in a solid block of steel. You would need a truly immense amount of force, something like a massive hammer strike. Spacetime is far more like that block of steel than it is like the pond. Its inherent stiffness means it takes the most violent, energetic events imaginable to set it ringing. This is why for decades gravitational waves remained undetected. We were not just missing the right technology, we were waiting for the universe to provide a signal loud enough to overcome the fundamental rigidity of reality itself. Only the most extreme cosmic engines can generate the power needed. A single star exploding in a supernova is not enough. Even a planet orbiting a star is far too weak. The only events that produce waves we can currently detect are the most catastrophic collisions, where objects of immense mass are accelerating to a significant fraction of the speed of light. The merger of two black holes, each dozens of times heavier than our Sun, acts as that cosmic hammer strike. For a brief moment, these collisions shake the very foundations of the cosmos, creating vibrations powerful enough to travel across billions of light years and still be felt, however faintly, here on Earth. This stiffness is not a flaw, it is a filter, ensuring that only the universe's most dramatic announcements ever reach our ears. Detecting a wobble smaller than a proton demands an instrument of almost impossible precision. This is the realm of the Laser Interferometer Gravitational Wave Observatory, or LIGO, a machine built to listen for the universe's faintest sighs. At its heart are two colossal facilities in the United States, separated by nearly 2,000 miles, one in Washington state and the other in Louisiana. Each observatory is shaped like a giant L, with two arms stretching 4 kilometers into the distance. Inside these long, vacuum-sealed tubes, scientists send beams of laser light racing back and forth. The core principle is one of exquisite comparison. A single laser beam is split in two, with one beam sent down each perpendicular arm. They travel to the ends, bounce off mirrors, and return to recombine. Under normal conditions, with no gravitational wave passing by, the two beams return perfectly out of sync, canceling each other out and producing no signal. But when a ripple in spacetime washes over the Earth, it does something profound. It very slightly stretches one arm of the L while simultaneously squeezing the other. This tiny, rhythmic warping changes the distance the laser beams travel just by a minuscule amount. That change is enough to disrupt the perfect cancellation. The two light beams no longer match up perfectly, and a tiny flicker of light, a signal, is born. The scale of this measurement is what defies belief. LIGO is designed to detect a change in the 4-kilometer arm length that is smaller than 1/10,000th the diameter of a proton. To grasp that, imagine scaling up the entire solar system. If our solar system were the size of a single atom, the distance LIGO measures would be the width of a human hair. Catching a vibration this small on a planet that is constantly shaking is the true engineering miracle. The entire system must be isolated from a cacophony of noise. Passing trucks, distant ocean waves, and even tiny earthquakes would easily drown out the cosmic signal. To achieve this silence, the key mirrors are suspended by sophisticated pendulum systems, isolating them from ground vibrations. The laser beams travel in the world's purest vacuum, ensuring no stray air molecules disturb their path. Even the microscopic jiggling of atoms within the mirrors themselves, caused by heat, is a source of noise. To quiet this thermal vibration, the mirrors are cooled to incredibly low temperatures. Every component is a masterpiece of isolation, all working in concert to create an island of perfect stillness, a quiet place where the faintest whisper of the cosmos can finally be heard. That quiet place where whispers are heard is not a single location, but a global network of ears listening to the cosmos. While LIGO made the first historic detection, it does not work alone. It is a key part of an international alliance of observatories, including the Virgo detector in Italy and the Kagra facility in Japan. Each of these instruments uses the same fundamental laser interferometer design, but they are spread across the globe for a reason far more important than simple redundancy. A single detector picking up a wobble is intriguing, but it could just be a local glitch, a passing train, or a small earthquake. When two detectors, separated by thousands of miles, record the same exact chirp at nearly the same instant, the signal is confirmed as real, a true cosmic event. But a third detector completes the puzzle in a spectacular way. With 3 or more observatories, scientists can perform a feat of cosmic triangulation. Imagine you hear a loud sound. With one ear, you know something happened. With 2 ears, you can roughly tell the direction it came from. But with a third person hearing the same sound from a different location, you can pinpoint its origin with incredible accuracy. This is precisely what happens with gravitational waves. The same ripple in spacetime will reach each detector at slightly different times, depending on its direction. By comparing the minute differences in arrival time at LIGO, Virgo, and Kagra, astronomers can trace the signal back to a specific patch of the sky. This triangulation was absolutely vital for the neutron star merger, GW170817. The LIGO detectors first sensed the signal, and data from Virgo, which registered a much weaker version of the wave, was essential for narrowing down the possible location from a vast swath of the cosmos to a much smaller region. This precise celestial address was then immediately sent to astronomers operating telescopes around the world, who swung their instruments to that exact spot and witnessed the brilliant kilonova fireworks show. Without this global network working in concert, that historic first light and sound show might have remained just another unconfirmed chirp in the data. These elusive cosmic giants have long haunted the edges of our galactic maps. For decades, astronomers knew of 2 main classes of black holes. There were stellar mass black holes, the remains of dead stars, typically weighing between 5 and 100 times the mass of our Sun. And then there were the supermassive behemoths, millions to billions of times the Sun's mass, lurking in the hearts of galaxies. But what existed in the vast chasm between them? This was the mystery of the intermediate mass black holes, hypothetical objects ranging from 100 to 100,000 solar masses. Their existence was a subject of intense debate, a missing link in the cosmic food chain. How did the small black holes grow so immensely to become the monsters at the center of galaxies? Gravitational waves have now delivered a definitive answer. In September 2020, the LIGO and Virgo observatories detected a signal unlike any other. It was the deep, resonant chirp of 2 black holes merging, but the final product was a colossal black hole of about 142 solar masses. This was the first clear, direct evidence of an intermediate mass black hole. The event itself was spectacular. It involved a black hole of 85 solar masses and one of 66 solar masses, a pairing that was already puzzling. The sheer size of the smaller one challenged our understanding of how stars collapse. Their merger created a gravitational wave signal that was both lower in frequency and longer in duration than any from stellar mass collisions, a drawn-out, rumbling crescendo that echoed the immense scales involved. This single detection confirmed that black holes can grow to these intermediate sizes through violent mergers, providing a crucial stepping stone in the evolutionary path to the supermassive giants. We now have proof that the universe builds its largest structures from a cascade of cosmic collisions, one violent merger at a time. The pristine simplicity of a black hole is a beautiful idea in physics. For decades, the prevailing theory was the no-hair theorem. This elegant concept suggested that a black hole, no matter how complex the star or gas cloud that formed it, could be completely described by just three simple numbers: its mass, its spin, and its electric charge. A black hole, according to this idea, had no other distinguishing features, no messy details, no individual personality. It was the ultimate cosmic bald head, a perfect void that erased all information about what fell into it, leaving behind only these three basic attributes. This was a tidy picture, but it led to a profound puzzle known as the information paradox. If a book falls into a black hole, is the information printed on its pages truly lost forever? This seemingly simple question threatens the very foundations of quantum physics, which states that information can never be completely destroyed. Gravitational waves are now offering a way to test this fundamental idea. The key lies in listening to the very end of a black hole collision, the ring-down phase. This is the moment when the newly formed, wobbling black hole settles into its final, silent form. According to the no-hair theorem, the ring-down should be a pure, clean tone, defined only by the final black hole's mass and spin. But what if the ring-down is not perfectly pure? What if there are faint, subtle overtones hidden in that final hum, like the complex harmonics of a struck bell? These extra vibrations could be the black hole's hair, subtle imprints in spacetime that encode a memory of what was lost inside. They might carry a faint echo of the properties of the original merging objects, or even a trace of all the matter and energy the black hole has consumed over its long life. Detecting this hair is one of the holy grails of gravitational wave science. It would mean that black holes are not the simple, featureless objects we once thought. They may have a hidden complexity, a subtle texture written on their event horizons that whispers the story of their violent past. Finding that whisper would not just rewrite our textbooks on black holes, it would be our first direct glimpse into the mysterious laws of quantum gravity, the place where the cosmic and the subatomic finally meet. The silent cosmos we once imagined is in fact a roaring symphony of collisions. Since that first historic detection in 2015, the data has painted a startling new picture. The universe is far noisier, far more violent than anyone had predicted. Our gravitational wave observatories are now catching major mergers with such regularity that astronomers have had to revise their cosmic census. Current estimates suggest that a significant event, a black hole or neutron star collision, occurs somewhere in the observable universe not every year or month, but every few minutes. Think about that for a moment. While you are reading this sentence, another pair of cosmic titans likely spiraled into each other in a galaxy far, far away. This constant background drumbeat of mergers reveals a universe teeming with binary systems, pairs of incredibly dense objects locked in a slow gravitational dance. It forces us to completely rethink the life cycle of the most massive stars. How do so many of them end their lives in these tightly bound pairs, avoiding the violent supernova explosions that might kick them apart? The high merger rate suggests that the pathways to forming these binary black holes and neutron stars are not rare, freak occurrences, but are instead a common, perhaps even dominant, fate for stellar corpses. Our galaxy and every galaxy must be filled with these invisible orbiting pairs, a hidden population slowly tightening their orbits over billions of years, waiting for their moment to collide and send a new set of ripples across the cosmos. This perfect transparency gives gravitational waves a profound advantage over light. While a single cloud of cosmic dust can completely obscure the most brilliant star from our view, that same cloud is utterly invisible to a passing gravitational wave. These ripples in spacetime do not interact with matter in the way that light does. Photons, the particles of light, are constantly absorbed, scattered, and blocked by the atoms and molecules they encounter on their long journey across the cosmos. This is why we cannot see the center of our own galaxy with optical telescopes. A thick veil of interstellar dust stands in the way. Gravitational waves, however, are a distortion of the stage itself, not actors upon it. They are waves of pure geometry, and they pass through planets, stars, and entire galaxies as if they were not even there. This unimpeded journey means they carry pristine, uncorrupted information from the most inaccessible places in the universe. Imagine trying to understand the heart of a raging storm by only looking at the clouds from the outside. That is the challenge of traditional astronomy. But gravitational waves allow us to feel the storm's very core, to sense the engine of chaos spinning deep within the cosmic murk. They can bring us signals from the seething inner edges of black hole accretion disks, regions of intense gravity and plasma that are completely opaque to every form of light, from radio waves to gamma rays. Even more remarkably, this transparency opens a window to the very dawn of time. The earliest universe was a hot, dense fog of particles that scattered light relentlessly. For hundreds of thousands of years after the Big Bang, the cosmos was a glowing, opaque plasma, and light from that era could not travel freely. But gravitational waves, born in the first frantic instance of creation, would have streamed right through that primordial soup, carrying a direct, unaltered story of the universe's violent birth. They are the only messengers that can reach us from that first, unimaginable moment, bringing us a whisper from the very edge of existence itself. Our current detectors are listening to the universe from the bottom of a turbulent ocean. The constant jitter of our planet, from rumbling tectonic plates to the gentle lapping of waves, creates a low-frequency hum that drowns out the universe's deepest voices. To hear those, we must ascend to the silence of space. This is the ambitious goal of the Laser Interferometer Space Antenna, or LISA, a mission being developed by the European Space Agency and NASA. Imagine a trio of identical spacecraft flying in a perfect triangular formation, trailing behind Earth in its orbit around the Sun. Each side of this triangle will be 2.5 million kilometers long, a distance so vast it could comfortably fit the entire orbit of the Moon. This will be the largest scientific instrument ever built, a gravitational wave observatory with arms 1 million times longer than LIGO. The principle is the same. Lasers will be shot between these free-flying spacecraft, measuring the tiny changes in distance as a gravitational wave passes by. But the scale of this instrument unlocks an entirely new spectrum of sound. By escaping Earth's constant vibrations, LISA will be exquisitely sensitive to low-frequency gravitational waves, the kind that rumble for months or even years. What will we hear in this new register? One of the most profound sources will be the mergers of supermassive black holes. These are the monsters that lie at the centers of galaxies, with masses millions or billions of times that of our Sun. When two galaxies collide, their central black holes are destined to meet, spiraling together in a slow, cosmic dance that can last for eons. LISA will detect these titanic mergers years, perhaps even decades, before they finally coalesce, giving us an unprecedented preview of the most energetic events in the modern universe. But the symphony does not stop there. LISA will also tune into the steady hum of millions of binary white dwarf stars within our own Milky Way. These are the fading embers of sun-like stars locked in tight orbits. Their collective, rhythmic chirping will create a constant background chorus, a gravitational hum that will allow us to map the invisible structure of our galaxy in an entirely new way. And perhaps most tantalizing of all, LISA might be sensitive enough to detect the faintest possible whisper, the primordial gravitational waves generated in the first instance after the Big Bang. This would be the ultimate prize, a direct recording of the birth of spacetime itself, a sound from the very beginning of everything. While LIGO listens for the high-pitched chirps of stellar collisions, another kind of observatory is tuning into the universe's deepest bass notes. This method uses natural cosmic lighthouses known as pulsars. When a massive star dies in a supernova, its core can collapse into a neutron star spinning at an incredible rate, hundreds of times per second. This rapidly spinning, highly magnetized object beams out radiation from its poles, and if that beam sweeps across the Earth, we observe it as a regular, repeating pulse of radio waves. The timing of these pulses is astoundingly precise, rivaling the accuracy of atomic clocks. A network of radio telescopes across the globe is now constantly monitoring dozens of these pulsars, creating what is known as a pulsar timing array. The goal is not to detect a single, loud event, but to listen for a subtle, persistent hum in the fabric of spacetime itself. The concept is one of supreme patience. Imagine the entire Milky Way galaxy as a vast, still lake, and each pulsar is a buoy floating on its surface. A passing gravitational wave, a ripple in this cosmic lake, would cause the distance between the buoys and our telescopes to minutely change. This would cause the arrival time of the pulsar's clock-like ticks to shift, arriving slightly early or slightly late in a predictable pattern across the sky. The gravitational waves these arrays are seeking are of an entirely different class. They are not the high-frequency chirps from stellar mass black holes, but low-frequency rumbles with wavelengths so long it can take years for a single wave to pass by. The most likely source of this cosmic hum is the combined din of millions of pairs of supermassive black holes. At the heart of nearly every galaxy, including our own Milky Way, sits one of these colossal objects. When galaxies merge, their central black holes are drawn together, beginning an orbital dance that can last for millions of years before they finally collide. Across the entire cosmos, countless pairs of these orbiting giants are continuously stretching and squeezing spacetime, each contributing its own faint tone to a universal chorus. This is not the sound of a single crash, but the collective vibration of the universe's largest structures, a background hum that has been resonating since the first galaxies formed. The violent mergers we witness are rewriting the rules of stellar death. A surprising pattern has emerged from the chorus of black hole collisions, one that challenges our most fundamental ideas about how these objects are born. The data reveals that many of these stellar mass black holes are spinning at breakneck speeds, approaching the maximum rate allowed by the laws of physics. This creates a cosmic puzzle. When a massive star dies, its outer layers are blasted away in a supernova explosion, while its core collapses under its own immense gravity to form a black hole. For the resulting black hole to spin this rapidly, the original star's core must have been rotating at a similarly incredible pace. Think of an ice skater pulling in their arms to spin faster, a principle known as the conservation of angular momentum. But here is the problem: the collapsing core of a dying star faces a powerful braking mechanism. The intense magnetic fields locked within the star's material should act like an anchor in an invisible sea, transferring rotational energy outward and slowing the spin long before the final collapse into a black hole. Standard models of stellar core collapse struggle to explain how a star could possibly transfer so much of its spin to its core without this magnetic braking effect intervening. How did these black holes get their whirl? Two compelling theories are now taking center stage. The first involves a cosmic partner. If a black hole is in a binary system with a normal star, it can act as a gravitational vampire, slowly siphoning material from its companion. This stolen gas doesn't just fall straight in, it spirals around the black hole, forming a hot, whirling disk. As this material finally crosses the event horizon, it transfers its own rotational momentum, effectively giving the black hole a steady spin, like pushing a merry-go-round over and over. The second theory suggests these fast spinners are born in the most crowded stellar neighborhoods, dense globular clusters where stars are packed together like commuters in a rush-hour subway. In this chaotic environment, black holes can form through direct collisions and mergers of smaller stars, a messy process that naturally imparts a tremendous amount of spin. Each new gravitational wave detection is another data point in this ongoing investigation, forcing us to reconsider the final, furious moments of a star's life and the turbulent environments where these dark titans are forged. Every single chirp from a cosmic collision is a direct challenge to Einstein's legacy. When the gravitational wave signal from a black hole merger arrives, it carries with it a precise prediction of how spacetime should behave under the most extreme conditions imaginable. Scientists compare the actual signal, the exact shape and timing of the chirp and ring down, against the complex equations of general relativity. They are searching for the tiniest discrepancy, a subtle wiggle in the data that Einstein's theory cannot explain. This is not a test in a gentle laboratory, it is a probe of the strong gravity regime, the warped space within the final orbits of a black hole merger, where gravity is at its most powerful and the rules of physics are pushed to their absolute limit. So far, against all odds, general relativity has emerged unscathed. Every single detection, from the very first to the most recent, has matched Einstein's 100-year-old predictions with astonishing precision. The theory has passed every test with flying colors, proving its robustness even in the face of these cosmic monsters. Yet this perfect record is in a way a tantalizing puzzle. Physicists know that general relativity, for all its beauty, is incomplete. It describes the force of gravity on a large scale, but it cannot be reconciled with the rules that govern the very small, the quantum world. Somewhere in the most violent possible environment, these two sets of laws must meet and merge into a single theory of quantum gravity. The intense, chaotic crucible of a black hole merger is the most likely place to find the first crack in Einstein's magnificent edifice. A future detection, perhaps from an even more massive collision or one observed with incredible sensitivity, might finally reveal a deviation. That tiny, anomalous ripple in the data would be the most exciting discovery in modern physics, a whisper from a realm beyond Einstein, pointing the way toward a deeper understanding of reality itself. These gravitational wave signals are delivering cosmic surprises, rewriting the very rules of how stars die. One of the most startling revelations came from that first detection itself, the merger that created a black hole of 62 solar masses. The two original black holes were already colossal, one at 36 and the other at 29 times the mass of our Sun, but the real puzzle lay with the larger one. According to established theory, the most massive stars should end their lives in a specific kind of supernova explosion, known as a pair instability supernova, that is so violent it leaves absolutely nothing behind, not even a black hole. This creates a predicted desert in the cosmos, a forbidden zone called the upper mass gap, stretching from about 65 to 120 solar masses. Theory insisted that black holes simply should not exist in this range if they formed from a single, collapsing star, yet our detectors keep finding them. The universe is clearly building black holes in this forbidden zone, and we are forced to ask how. The answer may lie in previous mergers. Perhaps these unexpectedly heavy black holes are not first-generation stars at all, but are themselves the products of earlier, unseen collisions in dense star clusters. A smaller black hole could merge with another, leapfrogging over the mass gap and creating a new object that then waits for its next partner. This suggests a hidden family tree of violence, with black holes growing generation by generation through a series of cosmic hookups. But the surprises do not stop at the high end. There is also a lower mass gap, a mysterious void between the heaviest neutron stars, around 2.5 solar masses, and the very lightest black holes, starting around 5 solar masses. For decades, this gap was empty, a quiet no-man's land in the stellar graveyard. What happens in a supernova to prevent a remnant from forming in this specific weight class? Does the physics of collapse simply skip over it? Now, gravitational waves are beginning to populate this desert too. The detection of a black hole merger where one object was a puzzling 2.6 solar masses threw this into sharp relief. Was it the heaviest neutron star ever found or the lightest black hole? The signal alone could not say for sure, but its existence proves that nature is filling this gap with objects we never knew could exist. Each of these unexpected masses is a direct challenge to our models of supernova explosions, forcing physicists to reconsider the chaotic, violent processes that mark the end of a star's life. That same cosmic transparency that lets gravitational waves travel unscathed also opens the door to one of the most bizarre effects imaginable. We know that light can be bent by gravity, a phenomenon called gravitational lensing, where a massive galaxy acts as a cosmic magnifying glass, warping the space around it and distorting the images of galaxies behind it. But what about the gravitational waves themselves? Could these ripples in spacetime also be bent and warped by the gravity of massive objects they pass on their long journey to Earth? The answer is a resounding yes. If a gravitational wave travels close to a massive galaxy cluster, its path is not a straight line. The immense gravity of the cluster curves the very fabric the wave is traveling through, bending its trajectory just as it would bend a beam of light. This gravitational lensing of a gravitational wave is a truly meta-concept, a distortion of a distortion. The consequences are profound. Just as with light, the lensing can create multiple pathways for the wave to reach us. Instead of a single chirp, our detectors might register 2 or more identical signals arriving at slightly different times, like a cosmic echo. The wave could also be amplified, its signal made louder and clearer by the gravitational focus of the intervening mass. This is not just a theoretical curiosity, it is a potential new window into the universe's greatest mystery, dark matter. We know dark matter exists because of its gravitational pull, but we have never directly seen it. It forms massive, invisible halos around galaxies and galaxy clusters, contributing the bulk of their gravity. A lensed gravitational wave carries a precise imprint of its entire journey. By analyzing the timing, the amplitude, and the number of these duplicated signals, scientists could essentially reverse engineer the path the wave took. They could map the precise distribution of mass in the lensing cluster, including the invisible dark matter that dominates its gravitational field. Detecting a lensed chirp would be like using a ripple in a pond to map the shape of an unseen obstacle it flowed around. It would give us a powerful new tool to chart the invisible scaffolding of the cosmos, using the whispers of black holes to illuminate the dark. Buried beneath the chorus of colliding black holes and neutron stars is a whisper from the very beginning of everything. This is the hunt for the primordial gravitational wave background, a faint, all-pervasive hum predicted to be the leftover echo of the Big Bang. In the first infinitesimal fraction of a second, the universe is thought to have undergone a period of hyper-accelerated expansion known as inflation, ballooning from a subatomic speck to a macroscopic cosmos in a blink. This violent, explosive stretching of spacetime itself would have sent powerful tremors rippling through the newborn universe, shaking the very fabric of reality. These primordial waves have been traveling ever since, their immense wavelengths now stretching across the entire observable universe. They form a stochastic background, a random, static-like signal that is not the sound of one single event, but the collective rumble of creation's first moment. Detecting this signal would be the ultimate confirmation of cosmic inflation, providing direct, tangible evidence for the theory that describes the universe's explosive birth. Think of it like this: the cosmic microwave background, the afterglow of the Big Bang we see as a faint microwave light across the sky, is a snapshot of the universe when it was 380,000 years old. It is a baby picture. The primordial gravitational wave background, however, would be a recording of the universe in its very first instant, a sound from its first cry. It is the only messenger that could have traveled unscathed through the hot, dense plasma of the early cosmos, carrying pristine information from a time before light could even travel freely. Finding this echo would not just confirm our theories, it would allow us to listen to the moment spacetime itself was born, tuning our instruments to the faintest possible vibration, the enduring memory of the universe's first and most powerful breath. These primordial whispers might not be the only relics from the universe's birth. To understand the next source, we must picture the cosmos not as a smooth fabric, but as a substance cooling and crystallizing. When water freezes, the process is not always perfect. Defects can form, tiny cracks and boundaries where the ice crystals misalign. Now, imagine the entire universe undergoing a similar phase transition as it expanded and cooled in its first frantic moments. These cosmic growing pains could have created flaws in the very structure of spacetime, one-dimensional cracks of pure energy known as cosmic strings. These are not strings in the everyday sense. A cosmic string would be an unimaginably thin filament, thinner than a proton, but it could be as long as a galaxy. Its density would be staggering, with a single inch of such a string potentially weighing more than a mountain range. A network of these cosmic defects, stretching across the universe like an invisible spiderweb, would be a fossil from a time before the first particles even formed. What makes them relevant to our story of gravitational waves is their potential for violence. Cosmic strings are not static. They can oscillate wildly, whip through space, or even develop sharp kinks known as cusps. When a cusp forms, a segment of the string can momentarily move at nearly the speed of light. This sudden, ultra-relativistic snap would release an enormous burst of gravitational waves, a sharp, powerful spike in the cosmic background hum. Unlike the chirp of a black hole merger, this signal would be a single, violent shout. Detecting such a burst would be one of the most profound discoveries in science. It would not just confirm the existence of cosmic strings, it would provide direct evidence for the grand unified theories of physics, offering a glimpse into the fundamental forces of nature when they were all one, moments after the birth of everything. We would be touching the very architecture of spacetime, uncovering a crack in reality itself from the universe's earliest infancy. That faint cosmic whisper is buried in a sea of noise. Isolating a signal that stretches spacetime by less than a proton's width is not just an engineering challenge, it is a monumental task of digital detective work. The raw data streaming from detectors like LIGO and Virgo is a chaotic mess, filled with the constant rumbling of the Earth, the vibration of machinery, and countless other false alarms that can perfectly mimic a gravitational wave chirp. Finding the real event is like trying to hear a single, specific whisper in a roaring football stadium. This is where the silent heroes of this scientific revolution come in, the supercomputers. These are not ordinary machines. To confirm a single detection, scientists must perform billions of calculations, comparing the incoming data against a vast library of predicted waveforms. Each of these templates is a precise mathematical prediction of what a gravitational wave from a specific type of collision should look like, calculated from Einstein's equations. Creating just one of these templates can require millions of hours of processing time on some of the world's most powerful supercomputers. An entire global network of data centers, a distributed brain known as the Einstein telescope, is dedicated to this single purpose. The process is a cosmic version of facial recognition. The supercomputer takes the noisy signal and rapidly compares it, point by point, to every single template in its immense catalog, searching for a match. When it finds one with a high enough statistical significance, the alarm is raised. This is not a field driven by a lone astronomer at a telescope eyepiece. It is a symphony of physics, astronomy, and cutting-edge data science, a collaboration where algorithms sift through the static of our noisy planet to find the faint, ringing signature of a black hole's death a billion light-years away. Without this immense computational firepower, the universe's whispers would remain forever lost in the noise. One detection stands out as a true cosmic anomaly. In May of 2019, the LIGO and Virgo observatories picked up a signal that was unlike any other, a brief, low thud they named GW190521. It was not the familiar rising chirp of a typical black hole merger, but a short, powerful blip lasting less than a tenth of a second. This single, blunt sound was the echo of the most massive stellar mass black hole collision ever recorded. Two colossal black holes, one weighing in at 85 times the mass of our Sun and the other at 66, slammed together to create a final black hole of 142 solar masses. This final object was a landmark discovery, the first definitive intermediate mass black hole ever seen. But the real mystery was the larger of the two progenitors. At 85 solar masses, it sat squarely in the theoretical pair instability mass gap, a range where black holes were not supposed to exist. Its very presence challenged our understanding of how the most massive stars die. How could a black hole this heavy form if the supernova explosion that created it should have blown the entire star to pieces? One compelling theory suggests these are not first-generation black holes at all. Instead, they might be second-generation products, born from the mergers of smaller black holes within the chaotic core of a dense globular cluster. In such a crowded stellar environment, black holes could sink to the center, find partners, and merge. The resulting, heavier black hole would then lurk in the cluster, waiting for another partner. The 85 solar mass object could itself be the grandchild of earlier, unseen collisions. This would neatly explain how it leaped over the mass gap, a cosmic shortcut through stellar evolution. The signal's unusual shape adds another layer of intrigue. Its short, blip-like nature suggests the black holes may have been spinning in a wildly chaotic, precessing orbit, tumbling through space like a pair of mismatched tops as they plunged together. Or perhaps they merged from an orbit that was already almost circular, leading to a very brief, powerful signal. GW190521 remains a profound puzzle, a single, deep note in the cosmic symphony that tells us the life stories of black holes are far more complex and violent than we ever dreamed. Those cosmic collisions are more than just a violent spectacle, they are a new kind of cosmic ruler. Every gravitational wave signal carries within it a direct measure of its own distance. The loudness of the chirp, its amplitude, tells us how far away the cataclysm occurred. Think of a firecracker exploding in the night. If you see the flash and hear the bang, the time delay between the two tells you how far away it is. Gravitational waves offer a similar but far more fundamental way to gauge cosmic distances. By reading the precise shape of the wave, scientists can calculate the intrinsic strength of the collision, and by comparing that to how faint the signal is when it reaches us, they can determine the exact distance to the source, all without a single traditional measurement. This is a pure, direct distance derived from the laws of gravity themselves. Now combine that with the other piece of the puzzle. When astronomers find the host galaxy of the collision with optical telescopes, they can measure its redshift, the degree to which the light from that galaxy is stretched as the universe expands. This redshift gives us the galaxy's velocity, how fast it is moving away from us, and here is the magic formula. The Hubble constant, the rate at which the universe is expanding, is simply the velocity of a galaxy divided by its distance. With a gravitational wave event, we get both numbers from two completely independent sources, a distance from the gravity of the collision and a velocity from the light of the host galaxy. This creates a brand new, pristine method for measuring one of the most important numbers in all of cosmology. Yet this powerful new tool is not resolving an old debate, it is deepening it. Measurements of the Hubble constant from other methods, like observing the ancient cosmic microwave background, have long been in a subtle but persistent disagreement with measurements using closer objects like supernova. This is the Hubble tension, one of the biggest mysteries in modern astronomy. When scientists plug the numbers from gravitational wave events into their calculations, the results are tantalizing. They do not cleanly side with one camp or the other, but instead land somewhere in the middle, adding more data points to a confusing but thrilling graph. This growing tension is a strong hint that our standard model of cosmology, our understanding of the universe's composition and evolution, might be missing a crucial ingredient. Perhaps dark energy is not constant but changes over time. Maybe there is a new, unknown type of particle influencing the expansion. Each new chirp from a colliding neutron star or black hole is not just a story of destruction. It is a vote in a cosmic election, a data point that could eventually force us to rewrite the rules of the cosmos. The violent collision of neutron stars does more than forge gold. It probes the absolute limits of matter itself. Every neutron star is a cosmic tightrope walk, a city-sized sphere of ultra-dense material balancing between two terrifying fates. On one side, gravity is constantly trying to crush it into a point of infinite density, a black hole. On the other, a mysterious quantum force known as degeneracy pressure pushes back, preventing total collapse. The exact point where gravity finally wins is one of the most important numbers in astrophysics, the Tolman-Oppenheimer-Volkoff limit. This is the neutron star equivalent of the Chandrasekhar limit for white dwarf stars, the maximum possible mass a neutron star can support before it must collapse. For decades, this limit was purely theoretical, a number estimated to be somewhere between 2 and 3 times the mass of our Sun. But theoretical models alone could not pin it down. The true value depends on the nature of the neutron star's core, a place of such unimaginable pressure that atomic nuclei dissolve into a bizarre soup of subatomic particles. We call the rules governing this soup the equation of state, and it is this equation that determines how much weight the neutron star can bear. Is the core a perfect fluid of neutrons, or does it contain stranger things like free quarks or hyperons? Each possibility creates a different equation of state, and thus a different maximum mass. The neutron star merger GW170817 was a perfect natural experiment to test these ideas. By analyzing the gravitational wave signal, scientists could estimate the masses of the two colliding stars. The data suggested that the resulting object for a brief moment was a neutron star right at the edge of stability, with a mass around 2.7 times that of our Sun. Almost immediately, it collapsed into a black hole. This single observation immediately ruled out all the theoretical equations of state that predicted a maximum mass lower than that value. Any model that was too soft, that could not support a 2.7 solar mass object, was instantly invalidated. The universe had performed the ultimate stress test, showing us that neutron stars must be incredibly rigid to resist collapse at such immense weights. This means the matter inside them is stiffer and more repulsive than many physicists had predicted. We are now closer than ever to answering the fundamental question: what is the true nature of matter when it is squeezed to the brink of oblivion? The final, violent moments of a black hole merger can launch the resulting monster into the void. When two black holes spiral together and merge, the newborn black hole does not always remain peacefully at the scene of the collision. It can receive a tremendous kick, a gravitational recoil that sends it rocketing through space at thousands of kilometers per second. This cosmic cannon effect arises from an imbalance in the final moments of the merger. Gravitational waves carry away not just energy but also momentum. If the merger is perfectly symmetric, with two identical black holes merging head-on, the waves are emitted equally in all directions and the kick is zero. But nature is rarely so tidy. Most black hole pairs have different masses and spins, and their final plunge is a chaotic, lopsided affair. In these cases, the emission of gravitational waves is stronger in one direction than the others. Just as a rocket pushes forward by expelling exhaust backward, the new black hole is propelled in the opposite direction of the strongest gravitational wave burst. These kicks are not gentle nudges. The most powerful ones can exceed 5,000 kilometers per second, more than enough to overcome the gravitational pull of even the largest galaxies. A black hole born from such a violent union would be flung out of its galactic home, condemned to wander the immense dark emptiness between galaxies. This creates a hidden population of rogue black holes, invisible cosmic drifters traveling through intergalactic space. They are the ultimate ghosts, the solitary remnants of a cataclysm so powerful it exiled them from the stellar communities of their birth. What other cosmic refugees might be hiding in the vast, dark spaces between the stars? That difference in mass creates a profound shift in the cosmic soundtrack. The chirps from stellar mass black holes are the high-pitched screams of the universe, rapid-fire events that are over in less than a second. Their waves oscillate at tens to hundreds of times per second, a frequency range our own ears could almost hear if the sound were not carried through the fabric of space itself. This is the violent, quick world of stellar death that LIGO has opened for us. Now shift your perspective entirely. Imagine the slow, deep groan of a redwood tree growing over centuries. This is the domain of the supermassive black holes. When two of these galactic titans, each weighing millions or billions of suns, begin their final dance, they do not chirp. They hum. The gravitational waves they produce have wavelengths so long it can take years or even decades for a single, complete wave to pass by Earth. Their frequency is measured not in hertz but in nanohertz, a vibration so slow and deep it is more like a permanent, shifting tilt in the landscape of spacetime than a sound you could ever hear. This is not a brief signal, it is a change in the very climate of the cosmos. While LIGO listens for the sudden crack of a cosmic twig snapping, the pulsar timing arrays are trying to measure the gradual, bending sway of the entire forest. One observatory captures the instant of catastrophic violence, the other senses the slow, tectonic drift of the universe's largest structures, a bass note so low it has been resonating since the first galaxies merged. The faint hum of a black hole ring-down might be our first direct clue to the quantum nature of reality. While gravitational waves are a purely classical phenomenon, described perfectly by Einstein's general relativity, the act of detecting them pushes us straight into the bizarre quantum world. The mirrors in the LIGO detectors, for instance, are so isolated and so sensitive that they are affected by the quantum fluctuations of empty space itself. This is the quantum limit, a fundamental barrier where the very act of measurement creates an uncertainty, a tiny jitter that physicists must cleverly overcome to hear the cosmos. But the true quantum connection runs far deeper than the detectors. It lives at the heart of the events we are listening to, the final moments of a black hole merger. A black hole's event horizon is the ultimate frontier, the place where the smooth, geometric laws of general relativity, which govern the very large, collide with the fuzzy, probabilistic rules of quantum mechanics, which govern the very small. General relativity tells us that matter falling into a black hole is lost forever, its information erased from the universe. Quantum mechanics insists that information can never be truly destroyed. This is the famous information paradox, a fundamental contradiction that has puzzled physicists for half a century. The violent, chaotic merger of two black holes is the most extreme laboratory imaginable for testing this paradox. The gravitational waves produced in that final, furious collision and the subsequent ring-down may carry subtle imprints, tiny deviations from Einstein's predictions that reveal how information is preserved. Perhaps the event horizon has a quantum structure, a frothing sea of virtual particles that subtly alters the gravitational wave signal. Finding that tiny anomaly in the data would be like discovering the first word of a new language, the language of quantum gravity. It would show us that spacetime itself is not a smooth, continuous fabric, but is woven from something more fundamental, something discrete and quantum. Each collision we detect is not just a story of cosmic destruction. It is a potential message from the edge of our current understanding, a whisper about how the universe truly works at its most fundamental level. That single event, GW170817, was not just a discovery, it was a revolution in motion. For the first time in human history, we witnessed the same cosmic cataclysm through two entirely different senses. The gravitational wave observatories felt the spacetime shudder of the neutron star's final orbits, while telescopes across the planet and in space saw the brilliant aftermath across the entire electromagnetic spectrum. This was the true birth of multi-messenger astronomy. It was the moment we stopped being one-dimensional observers and became true cosmic detectives, equipped with a full forensic toolkit. The gravitational wave signal arrived first, a classic chirp that pinpointed the event's timing and the masses of the objects involved. Then, just 1.7 seconds later, the Fermi and Integral Space telescopes detected a powerful flash of gamma rays from the same region of the sky. This immediate one-two punch confirmed a long-held theory that merging neutron stars are the engines behind short gamma-ray bursts, some of the most energetic explosions since the Big Bang. But the show was only beginning. As observatories worldwide swiveled to the location, they witnessed a spectacle that unfolded over days and weeks. In visible light, the kilonova erupted, its color shifting dramatically from an initial intense blue to a deep, profound red. This color change was a direct visual of the cosmic alchemy at work. The blue light came from lighter elements blasted out at high speeds, while the red glow was the signature of heavy, newly forged elements like gold and platinum, absorbing light as they expanded and cooled. Meanwhile, X-ray telescopes saw a lingering afterglow, the result of the merger's jet of material slamming into the surrounding interstellar gas at nearly the speed of light. Weeks later, radio telescopes picked up this same interaction, painting a complete picture of the expanding debris field. By combining all these different messengers, scientists could reconstruct the event with a level of detail that would have been impossible with any single one. The gravitational waves told the story of the star's final dance. The light showed us the chemical elements created, and the X-rays and radio waves revealed the structure and power of the resulting explosion. This single event provided a textbook's worth of confirmation for theories spanning from nucleosynthesis to relativistic jet physics. It proved that when the universe speaks, it does so in many voices, and by learning to listen to them all at once, we can finally understand the full story. This cosmic puzzle was perfectly illustrated by a signal known as GW190814. On August 14, 2019, our detectors captured the merger of a 23 solar mass black hole with a much smaller, enigmatic partner. The smaller object was a compact mystery, weighing 2.6 times the mass of our Sun. This number is critical because it falls directly into the lower mass gap, the long-standing no-man's land between the heaviest possible neutron stars and the lightest known black holes. On one side of this divide, neutron stars are thought to collapse under their own weight somewhere around 2.5 solar masses. On the other side, the lightest black holes we had confidently identified started at around 5 solar masses. For years, this left a perplexing desert between 2.5 and 5 solar masses, a seemingly forbidden range for cosmic corpses. The 2.6 solar mass object of GW190814 landed right in the middle of this empty territory. So what exactly did the black hole merge with? The gravitational wave signal alone cannot tell us. It reveals the object's mass and its tidal deformability, a measure of how much it stretches in its partner's gravitational field. A neutron star being made of dense matter would stretch significantly, while a black hole, a point-like singularity, would not deform at all. The data for this object was inconclusive, sitting right on the edge of what our models predict for both possibilities. If it is a neutron star, it is the most massive one ever found, pushing the limits of how rigid neutron star matter can possibly be. Its existence would force us to completely rewrite the equation of state that describes matter at these incredible densities, requiring a stiffer, more repulsive force than we ever imagined to prevent immediate collapse. If, however, it is a black hole, then it is the lightest one ever detected, challenging our models of stellar core collapse and supernova explosions. How does a star die and leave behind such a relatively lightweight black hole, skipping over the neutron star phase entirely? This single, unidentified object forces us to confront the messy, imperfect processes of stellar death, suggesting that the boundaries we have drawn in our cosmic zoo may be far fuzzier than our elegant theories predicted. Even the echoes of these cosmic crashes leave a permanent scar on reality. When a powerful gravitational wave washes over a region of space, it does not simply stretch and squeeze the fabric and then retreat, leaving everything exactly as it was. There is a subtle, irreversible effect known as gravitational wave memory. After the wave has passed, spacetime does not perfectly spring back to its original shape. It is left permanently, infinitesimally stretched in one direction, as if the universe itself has been slightly deformed by the event. Think of it like pressing your finger into a ball of soft clay. When you pull your finger away, the clay mostly regains its shape, but a faint indentation remains. That indentation is the memory, a lasting imprint of the force that was applied. For a gravitational wave, this memory is the permanent warping left by the immense energy and momentum carried away from the collision. It is a direct physical reminder that the universe has been fundamentally altered by a cataclysm billions of light years away. This effect is so incredibly faint that it has not yet been directly detected with our current observatories. The permanent distortion from even the strongest wave is smaller than the width of an atom over the distance from the Earth to the Sun. Yet its existence is a firm prediction of Einstein's theory, a consequence of the nonlinear nature of gravity, where gravity itself can generate more gravity. Successfully measuring this memory would be a monumental achievement. It would provide a completely new and unique test of general relativity, probing its predictions in a regime we have never before explored. It would also offer a new way to study the properties of the merging objects, as the precise nature of the memory is tied to the total energy and momentum radiated in the event. Finding this faint scar would mean we are not just hearing the universe's loudest crashes, but we are also learning to read the permanent writing they leave behind on the cosmos. Behind every cosmic whisper is a global chorus of human listeners. While the discovery of gravitational waves feels like a sudden breakthrough, it is in truth the product of thousands of dedicated scientists, engineers, and data analysts working for decades. This monumental effort is not driven by a few individuals in lab coats, but by a vast international collaboration where each person plays a critical role. Engineers design the impossibly precise mirrors and vacuum systems that isolate the experiment from a noisy world. Data scientists write the complex algorithms that clean the signal of Earth's constant rumbling. And theorists create the millions of waveform templates that allow supercomputers to match a faint ripple to a specific cosmic collision. It is a symphony of human expertise, all focused on hearing the universe's faintest sighs. But the most remarkable part of this story is that you, the public, can be a part of it. Through projects like Einstein at Home, anyone with a computer and an internet connection can contribute to this cosmic search. The concept is beautifully simple. The amount of data generated by these observatories is staggering, far too much for any single supercomputer to process in a timely manner. So the task is distributed. volunteers install a small program on their personal computers that runs in the background, using idle processing power to analyze tiny chunks of gravitational wave data. When your computer is just sitting there, screensaver on, it is actively helping to sift through the cosmic static, searching for the hidden signature of a black hole merger. Your laptop becomes a single neuron in a global brain, a distributed network of millions of machines working together to solve one of the universe's greatest puzzles. Every time a volunteer's computer helps identify a new signal, that person is credited as a co-author on the resulting scientific paper, making them a true citizen scientist and a direct participant in the age of gravitational wave discovery. This transforms the search from a remote academic pursuit into a shared human endeavor, where the collective power of our curiosity helps us listen to the stars. That faint chirp you have been hearing is not just a scientific concept, it is an actual sound you can listen to. Scientists have taken the data from gravitational wave signals and converted them directly into audio, a process called sonification. This is not a random musical interpretation, it is a direct translation of the universe's language. The frequency of the gravitational wave, how many times it oscillates each second, is mapped directly to the pitch of the sound you hear. As the two black holes spiral closer, their orbital speed increases and the frequency of the wave soars. This is why we hear that iconic rising chirp, a perfect audio representation of a runaway cosmic dance. Simultaneously, the amplitude of the wave, its strength, controls the volume. As the black holes whip around faster and get closer, the signal grows louder and louder, culminating in the final, powerful merger. This direct sonic mapping means that when you listen to that chirp, you are hearing the precise, unaltered rhythm of spacetime itself being stretched and squeezed by a cataclysm a billion light-years away. This act of sonification has done something remarkable. It has made the invisible violence of the cosmos accessible on a deeply human, emotional level. We can now not just understand the math, but feel the event, experiencing the terror and beauty of a black hole merger with our own ears, a visceral connection to the most extreme events in the universe. Our current detectors are listening from the bottom of a turbulent ocean, but the next generation will ascend to a silent mountain peak. The future of gravitational wave astronomy is being forged in the designs of colossal new observatories like the Einstein telescope and Cosmic Explorer. These are not mere upgrades, they are leaps into a new era of hearing. Imagine LIGO 4-kilometer arms scaled up to 40 kilometers or even longer, creating laser pathways of unimaginable precision. These future machines will be buried deeper, built with even more advanced seismic isolation, and cooled to temperatures near absolute zero to quiet the quantum jitter of atoms themselves. Their sensitivity will be so vastly improved that the cosmic chorus we hear today will explode into a roar. The Einstein telescope, planned deep underground in Europe, will have a triangular configuration of 3 separate detectors, making it 100 times more sensitive than our current network. Its American counterpart, Cosmic Explorer, envisions laser arms stretching 40 kilometers into the distance. With this power, they will not just hear the loudest, closest crashes. They will detect gravitational waves from the very edge of the observable universe, listening to the first black holes that ever formed. This new hearing will be so acute that it could potentially capture every single binary neutron star merger happening in the cosmos, a constant rolling thunder of cosmic alchemy. We will move from hearing a few loud voices in a crowd to listening to every individual conversation in a global stadium, transforming our understanding of the universe from a series of highlights into a complete, flowing narrative of cosmic evolution. That final collapse is one of the most violent events in the universe, yet it remains frustratingly silent to our gravitational ears. We are still waiting to hear the distinct burst of a core collapse supernova. When a massive star runs out of fuel, its core implodes under its own immense gravity, collapsing from a sphere the size of Earth down to a city-sized neutron star or a black hole in less than a second. This is the engine of a supernova explosion, and theory tells us it should be incredibly loud in gravitational waves, but only if the collapse is messy and lopsided. A perfectly spherical collapse would produce no waves at all. The reality, however, is far from perfect. The core is likely a churning, chaotic maelstrom. As it collapses, it may slosh and wobble violently. Neutrinos trapped in the dense material can create powerful convection currents, like a pot of water boiling over a star-sized flame. The newborn neutron star at the center might develop powerful oscillations, ringing like a bell struck by the hammer of gravity. All of this asymmetry, this cosmic imbalance, should shake the fabric of spacetime, sending out a short, complex burst of gravitational waves. Catching this signal would be like placing a stethoscope directly on the heart of the explosion. It would give us a direct view into the very moment a star's core turns into a neutron star, a process hidden deep within the expanding shroud of stellar debris that blinds our telescopes. The challenge is that every supernova is a unique and turbulent event. Unlike the clean, predictable chirp of two black holes merging, a supernova's gravitational wave signal is a messy, unpredictable shout. Our current detectors are listening, but they have not yet heard a signal clear enough to be certain. A single, unambiguous detection would revolutionize our understanding of stellar death, revealing the secret mechanics that power the universe's most brilliant explosions. The universe may be hiding objects even stranger than black holes. Beyond the familiar corpses of neutron stars and black holes, theoretical physics paints a picture of far more exotic possibilities, hypothetical entities that could completely reshape our understanding of matter and gravity. These are known as exotic compact objects, and they represent the ultimate frontier of cosmic weirdness. Imagine a star not made of atoms, but of billions upon billions of invisible particles all condensed into a single, ghostly sphere. This is a boson star, a gigantic object held together not by nuclear forces, but by the quantum rules that govern fundamental particles. Or consider a gravistar, a theoretical alternative to a black hole with a bizarre interior. Instead of a crushing singularity at its center, a gravistar might contain a core of dark energy, the same mysterious force accelerating the expansion of the universe, all enclosed within a thin, super-dense shell of ordinary matter. Then there is the quark star, a potential state of matter even denser than a neutron star, where the neutrons themselves have been squeezed so hard they dissolve into a seething soup of free quarks. For now, these objects live only in equations, but if they are real, their collisions would send out gravitational waves that initially look just like a black hole merger. Our detectors would hear the same rising chirp of a death spiral. The crucial difference would be in the final moments. When two black holes merge, the resulting object has a definitive event horizon, a point of no return. This creates a clean, abrupt ring-down signal that quickly fades to silence as the new black hole settles down. An exotic object, however, might not have such a perfect horizon. Without that absolute boundary, the merger's final moments could be very different. The gravitational wave signal might not end with a clean ring-down. Instead, we might hear echoes, faint, repeating whispers following the main crash, like a bell that continues to ring long after it has been struck. These echoes would be the signature of matter rebounding and vibrating against a hard surface, something that is impossible for a true black hole. Finding such a signal would be one of the most profound discoveries in science. It would mean that what we have been calling black holes might be something else entirely, objects with a tangible structure we can study. It would force a rewrite of the most fundamental laws of physics, proving that nature has even more incredible tricks hidden up its sleeve. Even the light from distant stars can be made to tremble by these cosmic ripples. A gravitational wave passing between us and a star does not just stretch space, it subtly shifts the star's apparent position in the sky. This is the astrometric wobble, a minuscule, rhythmic dance that future telescopes hope to track. Imagine a single star pinned against the black velvet of space. As a long wavelength gravitational wave rolls past, the fabric of space between us and that star is alternately stretched and squeezed. This warping acts like a shifting lens, causing the starlight to arrive at a slightly different angle. The star appears to jiggle back and forth in a precise, predictable pattern, tracing a tiny ellipse on the celestial sphere. The scale of this motion is almost vanishingly small. For the most powerful low-frequency waves, the shift would be measured in micro-arcseconds, a unit of angle so fine it is equivalent to spotting a human hair from a distance of over 1,000 kilometers. Detecting this requires a level of precision that is only now becoming possible. The European Space Agency's Gaia mission, which is meticulously mapping the positions and motions of over 1 billion stars, is laying the groundwork for this new kind of observation. By comparing the positions of vast numbers of stars over many years, scientists hope to find the correlated wobble that would betray the passage of a gravitational wave. This method is uniquely suited to the lowest frequencies, the same deep hum that pulsar timing arrays are seeking. But instead of listening for a timing glitch in a cosmic metronome, this technique watches for a synchronized sway in a field of celestial lanterns. A future mission, perhaps something like NASA's proposed Nanohertz Observatory, could be dedicated to this single, exquisite measurement. Success would give us a third, independent ear on the cosmos, turning the entire galaxy into a vast gravitational wave detector, where every star is a floating buoy on the rippling sea of spacetime. The smooth, silent merger of a black hole described by Einstein's equations hides a violent quantum secret. This is the heart of the black hole information paradox, a conflict between the cosmic laws of gravity and the subatomic rules of quantum mechanics. General relativity paints a serene picture. An astronaut crossing a black hole's event horizon would feel nothing special at first, passing silently into the void. All the complex information about what fell in, the atoms of a star, the pages of a book, would be seemingly erased, crushed into the singularity's three simple numbers: mass, spin, and charge. Yet quantum mechanics states with absolute certainty that information can never be truly destroyed. It can be scrambled, but it must be preserved. So where does the information go when it falls into a black hole? This is not just a philosophical puzzle, it threatens the very foundation of physics. To resolve this, some theorists have proposed a truly terrifying solution: the firewall. Instead of a peaceful horizon, the event horizon could be a seething wall of ultra-high-energy particles, a literal ring of fire that would instantly incinerate anything attempting to cross. This firewall would preserve information by preventing anything from actually entering the black hole in the first place, but it blatantly violates the smooth spacetime geometry demanded by general relativity. This is where the gravitational waves from a merger become crucial. The ring-down phase, that final, fading hum as the new black hole settles, is our only direct probe of the event horizon's nature. If the horizon is a perfect, smooth membrane, as Einstein predicted, the ring-down will be a pure, clean tone. But if a firewall or any other quantum structure exists, it could leave a subtle fingerprint on that signal. The ring-down might be accompanied by faint echoes, tiny repeating ripples following the main crash, like a bell struck against a textured surface instead of a smooth one. These echoes would be the signature of information rebounding, of a complex structure at the horizon that preserves the history of what fell in. Detecting that ghostly echo within the gravitational wave data would be our first direct evidence that black holes are not the simple voids we thought, but objects with a rich quantum texture that holds the universe's deepest secrets. Each collision we witness is a fossil from a different cosmic era. The black holes merging today were not born yesterday. Their story began billions of years ago in the hearts of massive, short-lived stars. By measuring the properties of these merging pairs, their masses, their spins, and the redshift of their signals, we are effectively reading a cosmic history book written in gravity. Each data point tells us about the environment and the conditions when the original stars were born, lived, and died. A higher abundance of particularly heavy black hole mergers at a certain redshift, for instance, points to a past golden age of star formation in the universe, an epoch where galaxies were churning out colossal stars in vast, dusty nurseries. The spins of the black holes are another chapter in this story. A black hole with a very high spin suggests its parent star lived a solitary life, spinning rapidly and collapsing without a partner to slow it down. In contrast, a black hole with little to no spin might have a more complex history, perhaps born from a binary system where tidal forces locked its rotation, or even from a previous chaotic merger that scrambled its original motion. This gravitational fossil record allows us to trace the life cycle of stars across billions of years, connecting the violent deaths we detect today to the ancient bursts of stellar birth that filled the early universe with its first generations of light. We are not just watching random crashes, we are piecing together the biography of the cosmos itself, one cataclysmic merger at a time. This invisible ocean of dark matter may be hiding its own violent collisions. For decades, the true nature of dark matter has been one of cosmology's greatest puzzles. We know it exists because of its gravitational pull on galaxies, but it does not emit or absorb any light, remaining utterly invisible to our telescopes. Now, gravitational waves offer a new way to hunt for it. One compelling theory suggests that dark matter is not a sea of exotic particles, but a population of ancient primordial black holes. These would not be the black holes formed from dying stars, but ones created in the first chaotic instance after the Big Bang, when dense patches of the infant universe collapsed directly into black holes of all sizes. If this is true, then some of the mergers we are already detecting could be these primordial dark matter candidates colliding. Their distinctive signature would be their mass. Primordial black holes could exist in weight classes that are impossible for stellar collapse, from as light as an asteroid to thousands of solar masses. Finding a black hole merger in one of these forbidden mass ranges would be a powerful hint that we are not just seeing stellar corpses, but the very stuff of dark matter itself. Even if dark matter is not made of black holes, its presence still leaves a mark on the ripples of spacetime. Imagine a gravitational wave traveling toward us from a distant galaxy. Its path is not through empty space, but through the vast, invisible halo of dark matter that surrounds every galaxy. Just as light is bent by a lens, the gravitational wave can be subtly distorted by the gravity of this dark matter. The wave's amplitude and phase could be minutely altered, and its travel time might be slightly delayed. These effects are incredibly faint, but future observatories with exquisite sensitivity could detect them. By studying how gravitational waves are affected on their journey to Earth, we could essentially use them as probes to map the distribution and clumpiness of dark matter throughout the cosmos. We would be tracing the invisible scaffolding of the universe by watching how it warps the echoes of its most violent events. This relentless search for cosmic whispers operates under a powerful principle, a promise of discovery so strong that physicists call it a no-lose theorem. It is the thrilling idea that our detectors have become so incredibly sensitive that they are virtually guaranteed to find something we do not expect. The universe is a vast and violent place, and we have only just begun to listen. For every cataclysm we have predicted, like colliding black holes or neutron stars, there are undoubtedly energetic phenomena we have not even dreamed of yet. The cosmos is filled with engines of destruction and creation that operate outside our current textbooks. This is not a hope, it is a near certainty born from the sheer power of our new sense. Think of it like building the world's most powerful microscope. You are confident you will see cells and bacteria, the things you know are there. But when you turn it on for the first time, you also discover an entire ecosystem of unknown, bizarre creatures swimming in a drop of water. Our gravitational wave observatories are that microscope for the fabric of reality itself. They are so finely tuned that they will inevitably pick up signals that defy our current models, vibrations that have no place in our catalogue of cosmic events. This could be the collision of an exotic object like a boson star, the snap of a cosmic string, or the faint hum of a dark matter particle annihilating in the heart of a galaxy. It might be a signal from a time before the first stars ignited, a relic from an era we can only theorize about. The no-lose theorem means that every moment of listening is an opportunity for a revolution. The next chirp that echoes through our detectors could be the one that forces us to throw out the old rules and write new ones, a single sound that redefines our place in a stranger and more wonderful universe than we ever imagined. These cosmic collisions are far from silent, invisible events in an empty void. The space surrounding a merging binary system becomes a crucible of extreme physics, a temporary forge of unimaginable violence. When the objects involved are neutron stars, the result is the spectacular kilonova we have already witnessed, a brilliant firework of heavy elements. But when the dancers are black holes, the effects are more subtle, yet equally profound. Picture a black hole binary nestled within a swirling disk of gas and dust, a remnant from its formation or material stolen from a companion star. As the two black holes spiral inward on their final approach, their dueling gravitational fields churn this surrounding disk into a frenzy. The space around them becomes a chaotic whirlpool of superheated plasma. When the black holes finally merge, the newborn black hole receives a powerful kick, a gravitational recoil that can send it shooting through this disk at immense speed. This is like a cannonball blasting through water, the surrounding gas, suddenly disrupted and compressed by this moving gravitational anchor, heats up to millions of degrees in an instant. This can trigger a brilliant flare of X-rays or ultraviolet light, a transient flash that telescopes can potentially see. In other cases, the merger itself can launch powerful jets of plasma from the poles of the new black hole, beams of matter traveling at nearly the speed of light. These jets, if pointed toward Earth, are detected as short gamma-ray bursts, the universe's most powerful electromagnetic explosions since the Big Bang. So, while the black holes themselves emit no light, their violent union can light up the cosmic neighborhood, creating a fleeting electromagnetic counterpart to the gravitational wave chirp. This means a single event can announce itself through both the shudder of spacetime and a brilliant flash across the sky, two different messengers telling different parts of the same catastrophic story. The staggering weakness of gravity has haunted physicists for generations. Why is the force that holds entire galaxies together so incredibly feeble compared to the other fundamental forces, like electromagnetism? This is the hierarchy problem, a deep mystery about the very fabric of reality. To solve it, some of the most daring theories in physics propose that our universe is not the three-dimensional stage we perceive. They suggest the existence of hidden, extraspatial dimensions, curled up into shapes so tiny they have eluded every particle collider experiment. In this radical picture, gravity is not inherently weak. Its strength appears diluted because it is the only force that can leak out, spreading its influence into these unseen dimensions. This is where the silent whispers of gravitational waves become revolutionary. If these extra dimensions are real, they would subtly alter how gravitational waves travel across the vastness of space. As a ripple in space-time journeys for billions of years, a small part of its energy could seep into these hidden realms. The effect would be a gradual, almost imperceptible weakening of the wave, a loss of amplitude that deviates from the perfect predictions of Einstein's theory in our familiar three dimensions. Our most precise detectors are now listening for exactly this kind of anomaly. By comparing the observed strength of a gravitational wave signal from a known distance against what our models say it should be, scientists can hunt for the telltale sign of energy leaking away. It would be like hearing the sound of a distant bell, but noticing its echo is fainter than it should be, as if some of the sound were vanishing into an invisible room. Finding such a discrepancy would be more than just a new discovery. It would be our first direct evidence that the cosmos is constructed with more dimensions than we can see, fundamentally reshaping our understanding of space, time, and the universe's hidden architecture. Every ripple we detect is a message from a different era in cosmic history. The gravitational waves from a collision a billion light-years away did not just travel across a vast distance, they also traveled across an immense span of time. We are witnessing that cataclysm not as it is today, but as it was when the universe was billions of years younger, a relic from an age when galaxies were still actively assembling. This transforms our observatories into a unique kind of time machine, one that does not look back with light but listens back with gravity. Light can be absorbed or scattered by interstellar dust, but these space-time tremors arrive pristine and unaltered, carrying a direct recording of the universe's violent youth. When we hear the chirp of two black holes merging, we are not just hearing their death spiral, we are eavesdropping on a chapter of cosmic evolution that has long since passed. This allows us to conduct a census of stellar deaths across the eons. By measuring the rate and properties of these ancient mergers, we can understand how the population of black holes and neutron stars has changed over time. Did the early universe, with its purer, more massive stars, produce heavier black holes than it does today? The signals washing over us now hold the answer, a fossil record of cosmic violence written not in stone, but in the vibrating fabric of space itself. Each detection is a piece of a grand historical puzzle, revealing how the universe has choreographed its most dramatic dances from its fiery beginnings to the present day. This signal arrives as a pure distillation of gravity itself. Unlike the light from a supernova or a gamma-ray burst, which is filtered through a chaotic storm of nuclear reactions, magnetic fields, and swirling plasma, a gravitational wave is a direct imprint of the event's geometry. It carries information that is untainted by the complex physics of matter. Think of the difference between trying to understand a thunderstorm by watching the lightning versus feeling the deep, resonant thunder that shakes your chest. The lightning is brilliant, but it is a complex discharge shaped by the atmosphere's electrical properties. The thunder is a simpler, more fundamental pressure wave traveling through the air itself. In the same way, the light from a cosmic collision is a spectacular but messy byproduct, while the gravitational wave is the essential vibration of the stage upon which the drama unfolded. This purity is what allows for such breathtaking precision. When scientists analyze that chirp, they are measuring the dynamics of spacetime with minimal interference. They can determine the masses of the colliding black holes to within a few percent, and deduce their spins with an accuracy that would be impossible if they had to first untangle a web of nuclear physics and radiation hydrodynamics. The signal is a clean readout of the universe's most fundamental force, offering a direct line to the heart of the cataclysm, unobscured by the brilliant but complicated fireworks that often accompany it. The monumental effort to hear the universe's faintest whispers has quietly revolutionized technology right here on Earth. That quest to measure a vibration smaller than a proton has forced engineers and physicists to push the boundaries of the possible, creating a cascade of innovations that now touch our daily lives. The lasers at the heart of LIGO are a perfect example. To ensure a perfectly pure beam, scientists had to eliminate minuscule power fluctuations that were once considered negligible. The solution was a revolutionary laser stabilization technique, a system that maintains a beam of such constant intensity and frequency it is essentially perfect. This technology is now being adapted for use in advanced eye surgery, where its unparalleled stability allows for cleaner, more precise incisions, protecting delicate surrounding tissue and improving patient outcomes. The same laser purity is also finding a home in manufacturing, where it enables the creation of microscopic features on computer chips with astonishing accuracy. Perhaps the most profound challenge was creating a sanctuary of silence on a trembling planet. The sophisticated vibration isolation systems developed for LIGO mirrors, which hang like the world's most still pendulums, have become a blueprint for ultra-precision. Imagine a factory floor where the slightest tremor can ruin the manufacture of a delicate component, like a microscopic medical implant or a sensor for a self-driving car. The principles born in the vacuum chambers of a gravitational wave observatory are now being used to create industrial workstations that are immune to vibrations from passing trucks or even distant earthquakes. This allows for a level of precision manufacturing that was previously unthinkable. Even the creation of LIGO Monumental Vacuum System, the largest ultra-high vacuum vessel in the United States, drove advancements in sealing and pumping technologies. These improvements are now benefiting semiconductor factories, where creating a perfect, particle-free environment is essential for building the next generation of electronics. And then there is the data. The algorithms developed to find a single cosmic chirp in a roaring sea of terrestrial noise are masters of pattern recognition. These are not simple filters, they are intelligent systems that can learn and adapt. This same sophisticated software is now being deployed to analyze complex medical scans like MRIs and CT scans, helping doctors to identify the subtle, early signatures of diseases like cancer that the human eye might easily miss. The techniques for cleaning a gravitational wave signal are being used to sharpen astronomical images from other telescopes and even to improve the clarity of satellite communications. This is the hidden legacy of the search for gravitational waves, a story not just of cosmic discovery but of earthly ingenuity. It demonstrates a beautiful and powerful truth that when we reach for the stars to answer fundamental questions about our universe, the technology we are forced to invent along the way often finds its most profound impact right here at home, quietly improving our health, our industry, and our future. We are living in the golden age of cosmic listening. A mere century has passed since Einstein first wrote down the equations predicting these ripples, and now we have built the ears to hear them. Every single chirp from the dark is more than a new discovery. It is a fundamental piece of a grand cosmic puzzle falling into place. Each new signal refines our maps of the invisible universe, revealing the hidden population of black holes, the secret lives of neutron stars, and the very limits of matter itself. This is not a slow, patient science anymore. It is an accelerating revolution. The detectors we have today are already listening to a universe far noisier than we ever dreamed, and the next generation of observatories, like the Einstein telescope and Cosmic Explorer, will turn that chorus into a roar. They will hear the mergers of the very first black holes to form after the Big Bang, and they may even capture the faint, enduring hum from the birth of spacetime. The future promises a cosmos speaking to us not in occasional whispers, but in a continuous, flowing narrative. We are the first generation to hear the universe ring like a bell, and the symphony has only just begun. From a silent movie of distant lights, we have stepped into a universe alive with sound and motion. This journey through 50 astonishing facts has revealed a cosmos that rings, chirps, and hums with the echoes of its most violent events. We are no longer passive stargazers, but active listeners to a symphony of colliding black holes and forging neutron stars. We have felt space-time itself stretch and squeeze, traced the origin of gold in a cataclysmic firework, and heard the death cries of stars from 1 billion years ago. Gravitational waves have handed us an entirely new sense, transforming our silent observation into a full sensory experience of the universe's raw power. And this is merely the opening note. The detectors of tomorrow will be so sensitive they will hear the first black holes ever born, and perhaps the very shudder of the Big Bang itself. So the next time you look up at the quiet night sky, remember the truth. That darkness is not silent. It is a roaring arena of gravity and time, a cosmic ocean constantly rippling with the stories of creation and destruction. We have built the ears to hear it. Your task is to stay curious, to keep looking up, and to listen for the whispers of the universe, for its greatest secrets are still waiting to be heard.